Welcome back. It's another inverse transform practice. This one's going to have distinct complex roots. It's going to be a cosine function, is what this distinct complex roots ends up being, really, in this case. All right, so we want to find f of t. Given big F of s, this frequency domain expression is 11s squared plus 172s plus 700 over s plus 2 times s squared plus 12s plus 100. So the denominator is not fully factored. It's partially factored. You've got this s plus 2, and then you've got this s squared, and then 12s and 100. But is it proper? Yes, it is, because if you multiply this all together on the bottom, you would end up with an s cubed term, which has a higher exponent order than the numerator. So it's a proper rational function. It's a rational function because it's a ratio, and it's proper because the order is higher on the bottom. And the book talks more about that. All right, so we have a quadratic we have to factor, and we've got this quadratic formula, right? So ax squared plus bx plus c equals 0. That's a quadratic, and the formula to get the roots is x equals minus b over 2a plus or minus the root b squared over 4a squared minus c over a. I like that form a little better for some reason. So we solve the quadratic. First thing you got to do is solve the quadratic. So s is minus 12 over 2 plus or minus root 12 squared over 4 minus 100. It's minus 6 plus or minus root 36 minus 100. So it's minus 6 plus or minus j8. The two roots. So we plug back in and do a plug in roots. Plug the roots back in and then do a partial fraction expansion. So the big F of s is 11s squared plus 172s plus 700 over our s plus 2 root. We just carry it over. And then now we just factor this quadratic and plug these roots in. So we get s plus 6 minus j8, s plus 6 plus j8. These are roots, so you got to do some sign flipping in there, right? So that's the plug in the roots into this big F of s. Then we set up an identity here, this three line equal symbol identity, and factor out these three roots. So k1 over s plus 2 plus k2 over s plus 6 minus j8 plus, now we can take a little shortcut here because we're doing complex roots, and for physically realizable circuits, that is any circuit that you could actually build, okay, we know that these complex roots will come in conjugate pairs, right? So this is kind of the thing you can do in engineering, is, just ignore math that you can't actually build something from. I'm going slow here. I got so the two roots, just making sure I carry those over. But the numerators the numerator constants will be in conjugate pairs. So I just did k2 and then k2 conjugate. So we know that's true because it has to be that way for physically realizable circuits. Some really smart engineer and math guy, figured that out for us. All right, so here's K1, just kind of shorthanding this a little bit. 11 s squared plus 172 s plus 700. And we're solving for k1, so the k1 term drops out of the denominator here, and you just get these two guys evaluated at s equals minus 2, the denominator of k1. That's going to give you k1, right? Just taking some shorthand steps. So plugging in this is a minus sign. Plugging in this minus 2, you're going to get 44 minus 344 plus 700 on the numerator, and you're going to get 4 minus j8 and 4 plus j8, plugging in this minus 2 in here. That's going to give you k1. And you can sort of see when you multiply these out that the j's are going to go away, right? Because you're going to get j squared, which is minus 1, and then you're going to get a minus j8 or j32 term and a positive j32, which will cancel. So the j's are going to go away, and you end up with a real number, which is just 5, right? So a real number. Okay, then k2, solving for k2, our numerator is 11s squared plus 172s plus 700 over, now here the this term here goes away, and so we just got this guy. So we got s plus 6 plus j8. This is negative sign parallel right here. There's so many opportunities to screw up a negative sign. Evaluated at s equals minus 6 plus j8. This thing, the opposite, you know, the values that'll make this denominator 0. What is that? Is that the pole or the 0? It's one of those two. Okay, the value that'll make the denominator go away. So be real careful with what you're canceling out here. In fact, let me just look this over. All right, this is going to give you the k2 value. And what is that? Working out the math, it's 11 times, evaluated at plugging in this value of s here. So let's plug it in and see what it looks like. Okay, that's s squared up here in the numerator plus 172 times that same thing, minus 6 plus j8 plus 700 over, plugging in s here, you're going to get minus 4 plus j8, plugging in this s into here and adding the 2, and then plugging this into that. The 6 cancels, and you get and the j, then you get 2 j8, so you end up with j16. This is going to be k2. So what is that? Like up here we got lucky and the j's went away and we just ended up with a real number, but that's not going to happen here. So here, calculator, all right? Just plug this stuff into your calculator, and you're going to, if you did that, you'd get 3 minus j4. All right, so the root, or the constant on top is a complex number. And we know that this other constant in this partial fraction term is going to be the complex conjugate. These constants always come in pairs. These complex constants always come in pairs. So if you have one, we must have another, and it's going to be this other k2. So it's right there. Therefore, k2 conjugate is 3 plus j4. Okay, so here's where we got to get a little bit like creative on the math. and take a couple of little leaps of faith here. So, you know, this whole J and E stuff is pretty crazy, right? It's pretty hard to even wrap your head around, but we have some notations that help. We've got this Phasor notation for 3 plus J4. So this one, the conjugate of that will 5 angle 53 for 3 plus J4 and then 3 minus J4. Okay, there's the two polar form conjugates. And then if you go back to chapter 9 and look at this, these phasors, it's a phasor, is really just shorthand for this business here. Right, 5 e to the minus j 53. So on this, so for the complex conjugate, it's going to be 5 e to the j 53, positive j 53. So it's okay to do this because this sort of bothered me when I was looking at this. But this is, I'm just going to. It's okay to use phasors. These are phasors. Remember phasors in chapter 9, they only applied to a constant frequency. But generally speaking, the reason we're using Laplace transforms is that the frequency can vary. But I think we're okay here because k's are constant. It's one of those things where, you know, the more you know on math, the deeper you are into your calculus stuff, the better your comfort level with what's going on there. So maybe I'm exposing my comfort level, but anywho, you can plug these constants. Okay, oh, did we solve for this? Yeah, 5. This thing is 5 over s plus 2 plus... So using this notation here for the K2 and the K2 conjugate, it's 5 e to the minus j 53 degrees over s plus 6 minus j 8 plus then this conjugate 5 e to the positive j 53 degrees over s plus 6 plus j 8. Yay! So is that fun or what? And then we've got a little f of t time domain to big F of s frequency domain rule. Our favorite rule, e to the minus at is 1 over s plus a. Let's use that rule like, you know, every day. You can use that rule. So we can go, you know, we can transform s back to t domain. We're going to do we're going to apply this inverse, what are we doing? What's going on here? Yeah, it looks like, it almost looked like time domain for a minute and it kind of freaked me out because I've got this E stuff, but it's still frequency domain. So now we're going to go back to time domain. You know, we're going from frequency to time domain. So we're applying this this rule here. We're going back. Just getting, you know, it's confusing, right? Because there's e's on both sides and stuff. So there's an e up in here. And so what's that look like? It's so f of t is this one. That's why this one's in here, because you could see it. That one's easy, right? Here, there's just a 5 on top, which we factor out, and then a is 2. So that's easy to see what we're doing here. But we're going to do that, this frequency to time, twice more. So factor out the 5. The whole thing, 5 e to the minus j 53 is a constant. Let's factor that out. Then we're left with, you know, 1 over this stuff where a is 6 minus j 8. So it's e to the minus at, where a is 6 minus j8t. Do that to the second term. Factor out the constant e to the minus j53 positive. Then you're left with 1 over this s plus 6 plus j root when you apply this rule to that. And you get e to the minus at, where a is 6 plus j8. Throw the t on there. That's it. So if you get through that and your brain's not hurting too much, we've got a time domain problem, but we can't plot it because it's got j's in it. You know, we can't plot j's in boring old human time domain. You know, we got to be like space, age, frequency domain. So we need to get rid of j's. So get rid of j's. And somebody did that for us already. This guy named Euler, right? He figured out a way to get rid of j's and put them back into the time domain. That's Euler's identity. Let me write that down there. From Euler's identity. If you take Euler's identity and manipulate it a little bit, you get this thing that I wonder why this thing isn't seen more often, but because I always throw, whatever. They give you Euler's, but I like this. This cosine theta in terms of these e's. Yeah. I guess, I don't know, I really like just plain old cosine and sine. Anyway, so this is from Euler's, and there's a sine one which may help you on your homework, right? For homework, go look that up or derive it from Euler's if you want. Euler. I never knew how to say Euler until the internet. And there's a website I found. You click on the little thing, and there's a voice that Euler. All right, where am I? Okay, so if we get this noise with all the e's, if we get it to look like this, we can apply this identity and get rid of the j's, and we're just in pure time domain. So f of t, make it. So basically, write it out. Make it look like that. All right, so f of t is 5 e to the minus 2t. That stays the same. So we can factor out this constant 5 e to the minus j53. That's no. The 6. Factor out this 5 and then e to the 6t, because that doesn't have a j in it, so that's cool. We can leave that guy, e to the minus 6t. You can leave that dude. Then what's left inside here, if you factor out the 5e to the minus 6t, you're left with our thing, this thing, the 53 thing, times e to the multiplying the minus sign in j8t. Okay, and then this term here, you have e to the j53 positive, and then e, and you have a minus j8t. Okay, then one more manipulation, 5 e to the minus 2t plus 5 e to the minus 6t times. Okay, then so you can add the exponents, right? There's a rule of exponents where you can add them. So this is j e to the j8t minus 53. Just adding these exponents and factoring out the j and keeping track of your minus signs. plenty of places to screw this up. Minus j 8t minus 53. Okay, it looks like that. It looks like this, where this is theta, right? That and that are theta. So we can apply this this identity down here. So this is 5 e to the minus 2t plus 5 e to the minus 6t. The half becomes a 2 cosine 8t minus 53 degrees. Okay, so then we apply this and come back. All right. And that's the answer. You can plot that. There's no j's in it. And I was curious, what does this even look like? So I plotted it, and you guys should plot everything. And it's really important. I mean, that's what we're trying to do. We're trying to. This is approximately 11. We're trying to get a feel for what do these signals look like. Are they bouncing? Are they decaying quickly? Are they, going to? Is there a spike? And that's what we're interested in. The time domain, right? What's happening in the time domain? So these graphs they're the real answer. I can't emphasize that enough. This thing here is just a bunch of math, and it's good to do math, but what the heck use is it? If I don't believe that very many people, if anybody, can look at these number values and visualize what the shape of the curve is gonna look like. It's just, I don't think, I'm not sure that's humanly possible unless you're one of those super genius people, perhaps. But the shape of the curve is extremely important. And nowadays there's so many tools that will do this for you that you should do it, because that's what we're really interested in. All right, what else can I say? So yeah, let's just go through review. So we have this rational function. It's a proper rational function, which is good. But this quadratic here has complex roots. So when we have these complex roots, we know that the constants of the partial fraction expansion will be complex conjugates as well. So we only need to solve for one of them. And so we go through this shorthand process to solve for these k constants, and then we get all of these, the 5, this, and this. You plug them back in, and be careful on what's a constant and what's an A and what's an S. Like these were your A's here. And this numerator is just a constant before you do the transform. And then after you do the transform, there's another way to kind of think about it, but on what you can factor out. Here you want to just factor out the 6's. Anyway, it's kind of weird. Good, really good problem to give you a feel for how these expansions go. And this is not a very complicated function, right? In the end. So that's what I've been trying to allude to, this idea of engineering versus math. Like there's enough to do there's enough to understand just in engineering to get your stuff to work. And so most people just kind of work on medium level problems, right? But the harder and harder problems require more and more sophisticated math, and people tend to bifurcate into either engineering type people or mathematics type people. And the people that can combine the high level sophisticated math and the engineering are rare. Those people are rare, and that's likely what you're going to experience in industry. I'm just telling you that so you just get a feel for the way the world is a little bit, or from my experience anyway. All right, I hope this was helpful to you. Thanks.